Okay, so we're happy to have Joan, Elias, Miró. He'll tell us about bridging positivity and S-matrix Bootstrap bounds. And let me just make an announcement. Next week will be Matt Walter, so make an announcement on Slack as well.
All right. Perfect. So thanks all Leonardo and to the organizers for the invitation to give this seminar. So the work I will talk about today is based on a paper that appeared recently in Archive and some ongoing work I'm doing with Miró and Mehmet Bumus, who is a PhD here at ICT. All right. So as many of you appreciate, quantum field theory is a very universal tool. However, due to causality and unitarity evolution, there are a bunch of constraints that apply on all the information that you can take in a quantum field theory. And perhaps the most famous one, or one of the most classic constraints, comes from positivity. And it's based on this classical example where you consider a derivatively coupled scalar that at leading quarter, the amplitude starts like so, with a c times s squared, where c is the Wilson coefficient of the Lagrangian. And now you can write this sum rule for the coefficient of this leading interaction, which is based on these dispersive relations, because you can represent c, this coefficient, as this small integral, I1, and in the limit where you send this radius of the integral to 0, this is exactly equal to c. And then, well, by Cauchy theorem, you can relate the integral I1 with I2 and I3. And now, under very general circumstances or general conditions, I3 vanishes, which is this residue at infinity, and the integral I2 converges both in the IR and in the UV. And the integral I2 is equal to the imaginary part of the amplitude, because you pick the discontinuity along the unitarity cuts on the real line. And this, in turn, by the optical theorem, is related to the cross section, and you are left with this positive integrand. And therefore, you conclude that C, this Wilson coefficient, must be positive. So this is a very classic example that I just wanted to mention to start getting into the same mindset. Now, another important or another example, if you wish, is provided by the recent results using the numerical S-matrix Bootstrap. Here, the prototypical or one of the simplest questions that you can ask is what is the maximal quartic of the amplitude? And now I will make some clarifications of what do I mean by this and how this is approached, and will serve as also as introduction for what I want to say later on. So here by quartic, what is meant is the value of the amplitude in the crossing symmetric point. All right. So this a point in the complex Mandelstam plane, which is below all the cuts that the amplitude develops because of unitarity. And now this becomes an optimization problem where you want to find the maximal and minimal values of this quantity subject to the constraints imposed by analyticity, crossing symmetry, and unitarity. Now, crossing symmetry is here defined for the case of a singlet particle. Unitarity, we all know what it is. And analyticity, there are various, I will make some clarification in the following slides of what are the various assumptions that go into here, okay? Now, this problem of finding the min-max value of this quantity as an optimization problem can be approached through two complementary strategies. One is it's so-called the primal, which is the original one by this set of authors that they started developing, and then there have been many other follow-ups. And here in the primal approach, the strategy is that you construct ansatz for the S-matrix, which encode these conditions, and then you use unitarity as a constraint while you try to find the min-max value. And the idea is that as you enrich more and more the ansatz, the space that you can explore with the primal will become larger and larger until you reach some convergence. And when this convergence is reached, then you claim that you have found the extremal amplitudes realizing these min-max values of the quantity of interest. So it proceeds by filling in the space of allowed amplitudes. On the other hand, the dual approach proceeds from this other complementary view, where what you do is you start excluding amplitudes that are unfeasible. So these are amplitudes that will have some large value of this quantity, but fail in realizing any of these conditions. And in this, then often, at least for the problems that have been studied so far, what one finds is that the duality, what is called the duality gap, the difference between primal and dual, becomes very small or negligible for the questions of interest. But I should say that this dual approach, which was started in this context of the S-matrix in these two-dimensional papers, and also in this higher dimensional paper, and also one by Kuczynski and He, this dual approach is much less developed. So I think we should pay more attention.
Can I ask a question, John?
Yes, please.
You don't cite on this slide the classic work from the 60s, 70s, which also proved some parts.
Yes.
Dual approach or primal approach, what they would do?
It's a dual approach.
How does it fit? But why do you not mention it here?
I didn't list it here because I'm not I was just citing the reference that are perhaps more useful if one wants to reconcile the rest of the talk, but it will appear, the reference will appear here.
No, but can you explain the difference between what was done in the old days and the current, what is done currently in the dual approach?
Yes, I will comment. Let me comment in 2 slides.
Okay.
On the previous work. Okay.
Thanks.
All right. So let me make some comments about the primal because it's the. So let me make one more comment because of the type of questions that have been asked so far in this context of the S-matrix Bootstrap. This difference between the dual bounds and the amplitudes found through the extremal through the primal approach. Because the difference is so small, a practical attitude that I will take, at least in part of the work that I will be presenting today, is to start looking for interesting physics using the primal approach. So, and then if we find something very interesting, then we'll go back and try to hammer down the rigor of that question, perhaps by bracketing with a dual approach. Okay. Now, let me make some more comments about the primal. So as I was saying before, one solves for crossing and analyticity by introducing some ansatz for the S-matrix. So this is one of the simplest answers that one can introduce, which works pretty well. And the idea is that first you solve by analyticity. So here in these ansatz here, one is assuming full or what is called maximal analyticity, and we consider that we consider like 3 separate planes, S, T, and U, and only at the end we take this slide of on-shellness, and each plane has a cut that goes from 4m squared to infinity, and otherwise it's analytic. So a way to solve for this condition is to define our amplitude through a convergent series expansion in terms of these raw variables. So if you are convergent in this analytic region, then this encodes a full analytic on the original S-plane. And this raw map is defined here that maps the whole plane to the unit disk, where 4m squared is mapped to 1. And crossing is solved because these coefficients are symmetric. So it's explicitly symmetric in STM. Now, unitarity is solved numerically. So what is typically done in this approach is that you decompose into partial waves and well, impose for unitarity in a grid of points in S, a fine grid. And then you look for convergence first in the extrapolation of the number of partial waves where you impose unitarity. And then once you know you have a unitarity amplitude, you start increasing the value of n. And you do so also until you reach some convergence in the angles, in the value of n. Okay. So running this machinery for the quartic coupling, you find this kind of result. So for the maximal coupling using the primal, you find this number, which is roughly 2.66. And an interesting point is that so here is the result from the 60s in this dashed line. This was revived recently by Guerrieri and Sever. And an interesting observation here is that what goes in to derive this dual, so what goes in to derive this primal bound, it's this maximal analyticity. And one may get worried that this is an unproved assumption, but what is interesting is that this red exclusion band only assume some proven analyticity, which is much more restricted. It only uses fixed T dispersion relations and for a small range of physical energies, only between 4 and 12.
Sorry, the red is dual and the green is primal?
That's right, that's right. And here is it's a zooming of this gap between the primal and the dual. And now the precise question that Slava was asking about why the old paper was here and the new one is here, I don't know it. Maybe if Guerrieri is connected, if Andrea is connected, he can say it. I don't know if it was because of they had much numerical power, or as far as I know,
well,
it was very similar.
If I can say like 2 words, with Amit, we systematized the approach so that we can even relaxing use SDPB to solve the problem. And the second thing is that we add the TU crossing, that in the original work of Lopez and Menesia, they were not adding the TU crossing that is not obvious in the fixed dispersion relations. That's why, including more constraints, we can do better, and also better numerics.
Very nice.
Right.
So but your assumptions are also weaker than maximum analyticity, right? You don't assume.
Yes.
I'm talking to Andrea's assumptions.
Yeah, but the answer is yes. But go ahead, Andrea, if you want to answer.
Yes, no, I was saying that we basically just use analyticity until we hit the large Lehmann ellipse. So we are very well.
You are only using proven analyticity.
Yes.
Is it fair to say that it's still a mystery of why the primal approach works so well?
Well, it's a mystery to understand for which questions it works well and for which one may fail. Yes, I agree. It seems that for these low energy questions, it does a very good job.
But why is this a mystery now? Because if this amplitude really exists, then okay, then you should be able to construct it also.
Well, but the assumptions are much stronger, right? They assume maximum analyticity, and also it's not clear what I thought there were some questions about what this amplitude being constructed actually converges to. It doesn't seem to converge to the physical amplitude, it converges to something a little bit more awkward, but I haven't looked at it in any detail, but
no.
I thought that people believe that for this amplitude maximum analyticity is actually true, so maybe the fact that it works well is the evidence for that this may be true.
Yeah.
Okay. Although this has not been proven. So.
Yes.
I mean,
all right.
I would still say that there's a bit of a surprise. It might be maximally analytic, but indeed, as Leonardo says, the primal approach does seem to converge to something wacky in the sense that unitarity.
Sorry, Baltier, I'm not hearing you well. Can you repeat? Hello.
So I'm changing microphones, maybe better.
Yeah.
So I'm I was going to say that there might be a bit of it might still be a bit surprising that it works so well, because indeed the primal approach does converge to something that's a little bit weird, in the sense that unitarity seems to be saturated for a whole, almost all energies that you check, and for all spins that you check. And you know that such an amplitude cannot exist because of Axe theorem. So we don't quite know what the limit of the primal approach gives. But when you look at the limit of the value of this coupling, then indeed it seems to approach precisely the...
Yeah, that was my impression, that it converged to something strange and nevertheless appears to saturate the bounds.
Yeah, I think I agree with that.
But
How about the amplitude which saturates the dual bound? Does it satisfy the expected properties?
I'm not sure it's easy to obtain a full amplitude from the dual approach.
So one comment. So with the dual, we are able to reconstruct the amplitude in a small region between 4 and 12, which is this region that we access. And in that region, primal and dual, they pretty much agree. Then you may wonder that maybe the awkward things, they happen at larger energies where these low energy observables are not sensitive.
Mm-hmm.
Thank you.
All right. So, all right. So today, what I want to I would like to present are some new S-matrix Bootstrap bounds for a theory with ON symmetry, and I will explain now next why this is interesting. But just as a reminder, so in this ON theory, I'm considering the 2-to-2 scattering of the two vectors under ON, and the amplitude decomposes in this way. We'll have annihilation channel, transmission, and reflection. In this case, crossing symmetry is encoded by the permutation symmetry in the TU components of this amplitude, and the same amplitude appears multiplying each of these tensor structures. Now, the starting point is that we will characterize the amplitude by the series expansion around some analytic point, and in particular, just for take a nice point, we'll take the crossing symmetric point. All right. Now, in the special case of the singlet, when we have the full crossing symmetry for STU, so the flavorless, this expansion looks like this. We have the quartic that I was referring to at the beginning, that we were just discussing, and then we have some higher order corrections. The first one that you can write down is this C2 coefficient, which if you want to match it into some field theory, would correspond to this dimension 8 operator. Then you can have order S cube terms, which is there is a single one that you can write down, which is this STU, and its coefficient we'll call C3. Now, as we'll see later, when one runs the primal approach, and also have some partial results already with the dual, you will find that the values that these coefficients can take lie inside this compact and convex shape, which touches in the origin, precisely because of the result I reviewed at the beginning, that C2 must be positive. And C2 equals 0 is only reached by the free theory, and in the free theory, then also the other guys are 0. Now, the field theory intuition for this theory, this applies around the origin, is given by this Lagrangian. And the point is that all these CI coefficients match to these GIs, okay, at 3 level, and up to higher order corrections that are either loop level or suppressed by powers of epsilon, which epsilon is simply m squared over the cutoff. And then here there is also this 3 level correction only because I'm expanding around the crossing symmetric point, which affects this quartic coefficient. Now,
Sorry, it's a possibly a very naive question.
Yes.
I'm a little surprised you're able to access the G0 coupling. Sorry.
Yeah. Yes, let me comment on that now.
Yeah.
It was the next slide. You're asking why on earth we can put a bound on C0? Or no, or
It's
G0?
because naively you would think that you need to do some subtraction.
Yes, I will go into this now.
Yeah.
But you could have asked me the same question perhaps before, right? Even here, because we're talking about the same constant. No?
I could have, but
Okay.
but now that there are concrete formulas, it jumped
Sure.
more concretely.
Yeah, more concretely. So the point is that one can write a subtracted dispersion relation, as you were saying, which looks like this. Okay. This is actually known by as Roy. This was done by Roy. This formula. Of course, his emphasis was different because he was interested only in pion physics back then. But when using this formula, so you should think of this formula as a sum rule. Okay. For an amplitude that satisfies the fixed T analyticity in S, you can write down you can express C0 in terms of this right-hand side equation. Okay. And what will happen is that when you take this equation and project into partial waves, okay, you will find that C0 is given by, so let's project into the spin 0 partial waves, okay? Because this subtraction constant here below the unitarity cuts is real, you will get an equation that looks like this, okay? Plus an integral over the absorptive parts, which will involve simply a sum over the spins, okay? Over the imaginary part of the spins times some kernel that you can compute out of this dispersion relation. And in this dispersion relation here comes only from blowing up this simple contour. Okay, so it's a fixed T. So you have dz over z minus s, let's say, of m of st over s squared. So you are guaranteed convergence when you blow up the contour by force are bound, and well, you will get some subtraction cost. Now, when you project this into partial waves, you get this contribution from the real part of the partial wave. So what this equation tells you is that if you want to access bounds on the quartic or operators that are more relevant than dimension 8 operators, you should bound also the real parts of the partial waves. Okay. This is a basic observation, but it will play an important role for the rest of the talk. Okay. Am I answering, Leonardo?
Yes, I need to think about it. I get the spirit. Yes.
Okay. Yeah, this is the intuition behind. Now, for the full ON flavorful case, the story is completely analogous. Now we will expand here the S-channel amplitude into also some quartic plus some linear. Now we have a linear correction. Before we didn't have it because of the full crossing, but now the crossing is slightly different, so we can have a linear correction, and this corresponds to dimension 6 operator. And now the intuition is very similar. One can take derivatives from this sum rule by Roy to access this coefficient CH. Okay. And again, this sum rule, if you project it into partial waves, you will see that you have real contributions. Well, it's already apparent here that there are real contributions. So if you don't bound real parts of the entering in the unitarity equation, you will have no bound for CH. Okay? While if you start bounding the real parts, there's at least some hope that you will find this bound. Now the filter intuition. So we'll find when we now run this exercise for general N, we'll find again this compact region, but now all of the boundary is strongly coupled, and it doesn't touch the origin of the space. Okay, and the filter intuition comes from a arrangement like this. even though there is no weak coupling here. If we reach weak coupling, it will be given by an arrangement like this, where the dimension, the linear correction that I was showing in the previous slide, this one here, okay, at tree level is given by this operator, okay, which is the dimension of this operator. And again, here all the coefficients are matched at tree level with the Wilson coefficients, plus higher order terms that are due to loops or powers of mass over the cutoff. Okay. I'm going a bit slow because I'm still on the motivation, but it's okay. Now, why I'm interested, one of the reasons one can be interested on this operator, on dimension 6 operators, is because they describe the leading deviation from standard model physics. And in particular, this operator that I was showing here, GH, is an important one because for n equal 4, okay, this describes the so-called custodial limit of the standard model. So it's a limit where we turn off Yukawa couplings and the hypercharged coupling. And well, this operator describes a universal deformation of all the couplings of the Higgs to any particle. And okay, because the Higgs agrees very much with the standard model so far, there are exclusion bounds for what is the value that this operator can take. And in units of 1 TeV, okay, now it depends slightly on the assumption that you put on the fit, but roughly the current fit tells you that this guy in units of 1 TeV cannot be larger than 1. Okay? Now, of course, this is a crude simplification of the actual physics, but the approach I will be taking, which is simply this Owen theory, can be easily made more realistic by studying SUN theories or by including Gauge interactions or Yukawa interactions. It will become more clear how to generalize it as I go on in the talk. Now, I was saying that this. Yes?
You're not using the fact that in the Higgs case, symmetry is spontaneously broken, and here it's not.
No, not yet, not yet. Here I'm imagining that I'm at very large energies, so corrections of the type that you are telling me will be suppressed by mass of the gauge bosons over the energy.
Yeah, but
of course you have a
massive. You do have a scattering of massive particles, and you have a full multiplet of massive multiplet of massive particles in your S-matrix setup. There's no such multiplet.
Exactly. So, well, there is the multiplet at large energies. There is the full O4 multiplet. I guess one complaint you could say early on is that here I have a mass. So one should be careful that the bounds one claims for this operator do not depend on this IR physics if I really want to claim it's a high energy bound. And this I will try to address it later on. Okay. So I move on. But sure, it's a fair point. Now, okay, as I was saying at the beginning, so we will find this kind of compact and convex region that does include the origin, but doesn't touch the origin, the boundary. And this is well known already from examples that were studied on these papers, where it's easy to construct weakly coupled theories that give either sign for this operator. So we know it's not a definite sign. Okay. Now, because I think that the bootstrap, the S-matrix Bootstrap provides already this nice hint. It provides this nice hint that they are saying something about the quartic, which is a much more relevant operator than the ones that are usually accessed by positivity. So this hint, of course, it's easy to realize then that it should also be able to say something about dimension 6 operators. So one of the big motivations for our work is to try to make this more precise, to use this S-matrix technology to put a bound on the dimension 6 operators. Now, when we'll find this, so the first part of the talk will be about finding these regions on the space of CIs. And now here we will not be able to claim victory yet, because along the whole boundary of this space, the difference between the values of the CIs and the Wilson coefficient is much larger than order 1. Okay, so in other words, the dots here are very large. okay, are very large. So even though this provides a bound on dimension 6, is impractical, okay? So the second step I would like to take.
Let me try to understand this point. So somehow it must be that the bound you're finding on these more relevant couplings come from the upper unitarity bound, right? From the fact that it's not just positivity, but it's also the fact that the partial waves are also bounded from above.
Yes, it's because we are not only looking at these two linear approximations to unitarity, but
right.
because also these two that you are saying. So you, I guess,
then,
by upper
correct.
you
but
mean
then implicitly you are a strong coupling, right? Because if you are a weak coupling, then you never access the
perfect. Yes,
and then of course you cannot match the Wilson coefficients because it's
yes, exactly. So
you can, I mean, that was guaranteed that you could not match with the Wilson coefficient because you are implicitly a strong coupling.
Let me just come. You're always asking me the question that is coming in the next slide. So
okay,
coming in the next slide. Okay.
Yes.
So precisely want to amend this caveat, okay? And you will need to wait a few more slides, but maybe I can already advance a bit that what we want to do is want to isolate from this space, okay, a tiny subspace that has a weak coupling interpretation in the IR, okay?
Yeah.
So for doing that, let me advance already the second part of the talk because maybe I will not arrive, but we like to put some bounds, okay, some extra constraints. So in the Bootstrap, if we want to isolate more physical theories, we need to put more constraints. And we would like to ask that the imaginary part of the amplitude or the cross section has a nice behavior in the IR, okay, up to some big cutoff, okay. And in this way, the CH coefficient, okay, in the IR will be given exactly by GH, okay. And in this way, we'll be able to interpret these new bounds here in this tiny region. This tiny region will have, sorry, this one over here, we'll have that here, GH, it's a roughly CH, okay? Up to tiny corrections that are controlled by our assumption on how small is the amplitude in the IR.
Okay.
So only then we'll be able to claim that this new space, so we'll isolate this space of effective field theory amplitudes, and then we'll be able to claim bounds on dimension 6 operators, okay? Or even marginal couplings. That's the idea. Okay? So
I see. That's a little surprising, right? Because you're saying that even a weak coupling, you're able to use the upper to somehow get some mileage from the upper limit.
No, you will see not surprising because because the mileage from the upper limit will come from the fact that when you look at the dispersive representations of these guys, plus the integral over the absorptive piece, okay? So some absorptive piece, you will see that this integral, even though it runs throughout all physical energies, is actually peaked only at high energies. Okay.
I think I should let you go. Sorry, I didn't want.
Let me go.
Derail your talk. Go ahead.
Okay. All right. So well, that was the motivation of what I want to do. I want to first find bounds on this space of CIs, and out of it extract those amplitudes that have some non-negligible IR cuts, but are maximally strongly coupled in the UB. Okay? That's the physical set. All right. So let me show you already some new results. So here it's for the singlet case, and I'm showing you the space on C0, C2. All right. So before the beginning of the talk, I was showing you the maximal quartic, which is the point A and B in this plot. Okay. And now we are just opening up some new direction on this space, which is C2. Okay. To get these results, we had to introduce a number of numerical improvements with respect to the original ansatz. Let me comment perhaps the two most important ones. First of all, the original answer, the original primal answer, as I was explaining at the beginning, involves some cutoff in the spin. And it's important to look for convergence in this spin cutoff. Okay. So a nice thing that one can do is, because we know that the amplitude is a positive for physical energies and for T on this region, because this positivity comes from the Legendre polynomials. Okay. And then what the extra constraint that we are adding is that for those partial waves that are not constrained already by the primal unitarity constraints, we ask that this difference is positive, and this results in a very nice convergence, and it's on the spin direction. And this it's a nice constraint, because in this region, okay, the Legendre polynomials are positive, so it's very constraining on all the partial waves, sum of positive things. And the second interesting improvement is that instead of the row ansatz expansion I was showing you before, we do an ansatz where we expand, if you wish, on resonances. Okay, on the position of the resonance. What we do is that the fixed point of the map that was going from the cut plane into the unit disk, we sum over different positions of the fixed point, and we don't understand precisely why, but well, there are some intuitive reasons why, but the only important point to notice is that for the problems that we are exploring, this has a much better convergence.
I actually don't understand this formula. What are these fixed points? What I didn't understand.
So in this formula, can you read this? So this impressionistic formula down here is supposed to be the conformal map from the cut plane to the unit disk. Okay, and okay, this map involves a parameter, okay, which tell us where are we mapping, say, for instance, the point for m squared. Okay.
Mm-hmm.
Okay. So what we are changing is this parameter, which the map depends upon. Okay. And now what we do is that this parameter, which can take values between, say, any value, can take any value between 4 and infinity. We take a grid of points for this parameter, and then we consider this richer answers. If you wish, a piece of intuition is that if you want to expand one of these maps in terms of the other, it involves infinitely many powers of the usual row expansion.
Okay.
Is it clear, the formula? Huh?
How did you come up with this? This looks very different from people were trying before. So this looks like a big conceptual leap. So how did you get from there to here? Well, I don't know, maybe you want to comment about this later.
Let's comment about this later, perhaps in the discussion session. And I will let also Andrea to comment on this, because he played a major role in having this idea of the wavelet-like expansion. Okay. Now let me comment on the physics that we find along the boundary of this space. Okay. Now between C and A, it looks like lambda phi 4 theory. Here it's like for negative lambda phi 4, and this would be like positive lambda phi. Okay. And there are some observables that we introduced to characterize this boundary. One is what we are calling simply like spin dominance. We take the usual sum rule for C2. So let me just remind you, it was introduced in the very first slide, but here for the massive case, the one that we are using looks something like this. For to infinity s minus 4/3 the cube of ms 4/3, okay? Now decompose this into partial waves, and then what we are looking is at the relative contribution of the spin 0 over the whole value of C2. Okay, and this, okay, this gives you a hint of which are the kind of theories living on the boundary, and a hint that it definitely is strongly coupled if you are dominated by many large spins, because we don't know how to write these theories with coupling. So from point A, okay, to see in this direction, most of the boundary is dominated by higher spins, and it's only on this small section that is dominated by spin 0. And if you think and just another comment. So, well, if you think on lambda phi 4, that is what you expect to live. So lambda phi 4 lives in the region here. Now, another observable that tells you that we are exploring here is only couplet physics on the boundary is this improvement was already introduced in the original S-matrix Bootstrap paper, which was to allow for threshold singularities. And what we can do is to follow this threshold singularity along the whole boundary. And what one sees is that in the upper branch, this threshold singularity, the coefficient of the singularity is put to large values, while in the lower branch is set to 0. Okay, which this also makes it compatible with lambda phi 4 in this segment here, because there we don't expect, if it's weakly coupled, it should not have any further singularity. I mean, in this region here. Okay, another obvious reason.
What's the physical meaning of this fact that this coefficient is? Yeah, I'm a bit confused. Can you comment?
Yes. So in the region here, the lambda the would-be lambda phi 4 field theory intuition, it's like maximally attractive. This theory here is for the wrong negative sign of the quartic. So it's like this, if you want to feel fair. And what the theory is trying to do is to put to generate some bound state, but since we are excluding bound states below threshold, the best it can do, the best optimal solution that it can find is to put it right at threshold. Yes. Note that in the region here, in this region here, the quartic is in the region here, as I was saying, the quartic is negative, okay, but it still is a good effective field theory because you can easily stabilize the quartic potential with a higher dimensional operators or whatever you want to put here. Okay, you can make it fully stable and still this guy is having 0 impact on the imaginary part of the amp. Now I don't know what time is it. Okay, I only have 45 minutes, so let me jump part of this. Okay, here are, maybe I can go through it in the discussion. It's related to the question that well, let me make some comments nevertheless about the dual approach. So as we know from analytical mechanics, it's nice to formalize optimization problems with Lagrangian. Okay, now in this Lagrangian there will be some objective, okay, which we are shooting radially. We are taking points inside this space, and we are looking for the maximal radius we can take starting from such point. And we need to impose some constraints due to unitarity and crossing. Okay. Now this piece here depends only on the imaginary parts of the amplitude through the dispersion relation. Okay. Unitarity, well, you know it very well. If we do some linear approximation, it will depend on imaginary and real parts, but they will decouple. These fields are not coupled in this part of the Lagrange. And now crossing, a nice way to treat it is through this fixed T dispersion relation. This is the dispersion relation I was introducing I was commenting at the beginning of the talk. And here I'm giving you the kernel. And this fixed dispersion relation incorporates automatically SU crossing symmetry. What it does not incorporate is the UT symmetry. Okay. Now, to incorporate UT symmetry, it was observed by Roy a long time ago, is that what you can do is just take this equation, which gives you the UT crossing, and plug in this equation this dispersive representation that is SU symmetry. Okay, you do so and you decompose in partial waves. Okay, and now this constraint is what is giving you the extra crossing that was missing in the dispersion relation. It's giving you the TU crossing. Okay. Now, a nice thing that you can do in this equation now, this looks more like the bootstrap crossing equation, because what you can now do is to take derivatives on this equation and and evaluate them on the crossing symmetric point. Okay. And the more derivatives you take, the more crossing you impose. And this way of encoding crossing that we're using in the work is completely equivalent to these null constraints that were introduced in these recent papers that exploited the full crossing. So this is how we did crossing, how we did crossing in the work. Okay. Now, let me jump into the second part of the EFT results, because otherwise I will not get into the main point. Okay. Now, the regions on the CIs, as I was saying, as I emphasized many times, most of the boundary of this plot is strongly coupled. I want to carve out from this region the weak couplet, the region that can be interpreted in terms of effective field theory operators. Now, ideally, we would like to set some constraint such that in the IR, our ansatz or our numerical our optimization problem in the IR, our amplitude is equal to some amplitude of choice that we're interested. Say we're interested in pion physics or in QCD or in the standard model. We would like to impose that in the IR we reproduce the theory of interest, and in the UV we allow for any crazy physics. Okay. Now this is hard to impose numerically, and also it's not very nice, because if we put this kind of constraint in the IR, then we will not be studying unitarity amplitudes, because we don't have we are messing too much with we are not allowing the real part to fluctuate. So instead, what we did here is that we do this convex relaxation and only impose this constraint. Okay. Actually, we'll impose an integrated version of this constraint. Okay, which is what I'm showing you here. This is the first method that we introduced in the work. So we'll rerun again these min-max optimization problems on the CIs, but asking that our amplitude in the IR is very weakly coupled. Now, for the case at hand, we will be taking simply some lambda phi 4 theory in the IR, and then the effective field theory amplitude is simply given by this square root. If you
Can
were
I ask a question?
Yes,
John. Is it really important that you have this less than or equal with coefficient 1? I mean, we cannot expect that this is going to be exactly with coefficient 1. There's going to be some small deviation for sure.
No, it's not very important in the sense that we can accommodate these variations in our choice of this parameter here in a way. Okay, because
Which
this will
parameter?
be in this parameter here. G0.
Okay.
It will be an input parameter. Okay.
Okay.
We will take it small, but
okay. Sounds good. Yeah.
Now there is another method which is quite cool, but I will not be reviewing today, which consists on imposing the constraint pointwise instead of this integrated version. Now the intuition from explorations that we did in 2 dimensions is that if you impose enough of these constraints for many ends, this is roughly equivalent to the pointwise constraint. But let me not comment more on the pointwise constraint for the moment. Now, so what do we get when we do this? When we do this, now we find this region, which is well inside the plot I was showing at the beginning for C2 versus C0, only that now I'm normalizing the axis in terms of the cutoff. Okay. Here I'm doing this exercise for some reasonable values, so some moderately weakly coupled quartic and some large enough ratio for M over the cutoff. I hope to get to the point where I can comment on the cutoff dependence, which will be in a couple of slides. Okay, but let me mention quickly some of the physics in this plot. Okay. Now, well, first of all, let me just make some obvious comment is that we don't expect from this game I'm showing here to find a bound on C0, because the result that we find here for C0 is equal to the G0 that we put in the input. So this is, if you wish, a basic cross-check, but okay, it's good that the obvious cross-check goes through, okay? So the same G0 that we input into the constraints come out roughly as the answer, okay?
Okay, sorry, maybe that resolves my confusion. I was confused by how you could get now you are making the weak coupling assumption, which are made in the positivity game of
exactly.
And then it would be very surprising to be able to get a bound on C0.
No, exactly. Okay, that's answering better your question before. Exactly. Here, there is no actual bound on C0, but there is an upper bound on C2. And know that if we are interested, as I am, in also dimension 6 operators, then I will be able to claim bounds by exactly doing the same game, okay? So I will show it later on, but...
So for dimension 6...
It's exactly the same logic. It's simply that it's a flavorful amplitude, and here in the y-axis...
Dimension 6 is something that you could have also accessed from the standard positivity dispersion relation?
No, not quite, because it involves subtraction constants. Okay? Remember that...
What is the magic that allows you to do better than that? That's basically my question.
The magic is precisely looking at the real parts of unitarity. That's the magic for dimension 6. That the dispersion relation for dimension 6, sorry if I'm getting this easy, but 1 second. The dimension 6 dispersion relation, it's given by this equation here. But this is a particular dispersion relation you can write down. This is the doubly subtracted dispersion relation that involves this subtracting constant. This you don't have it for dimension 8 in the positivity games. And now just project this equation into partial waves. CH is a scalar.
So are you saying that there should be a way to supplement the positivity game of Simon et al. With this additional piece?
For sure. Yes, exactly.
So, okay.
Yes,
of course, it's very nice to recover this as a limit of the fully non-perturbative thing, but what if I'm a perturbative person from the get-go? Then I could...
Exactly. Yeah, you will reproduce all that. It's what I will hit now.
Okay.
Precisely. Yeah. You are still managing to always go one slide before. So that's exactly what I want to say next, okay? So let me make some comments about this effective field theory region, okay? Now, there is a nice observable, which we call simply R, which is the ratio between the contribution to from the UV to C2 and the full C2, okay? Where C2, I wrote it a few slides above, but C2, it's simply the integral over the whole physical energies, okay? Now, this ratio tells you if the ratio is 1, okay, it means you are fully UV dominated, okay? If the ratio is 0, it means that you are IR dominated, okay? That's the intuition. This has nothing to do with weak or strong coupling, okay? It just tells you the relative contributions, and you could imagine weakly coupled theories where you achieve R equal 1 or R equal 0, okay? But okay, and then we can also look at the ratio of C3 over C2, which has received recent attention thanks to the positivity, these double-sided bounds by Caron et al. And Tolle et al. And let me tell you what we find here. So first of all, you can derive a very simple bound. This is not a big thing, but it's useful to compare with the bootstrap, which is given by this equation here. Okay. Now C3 is given by this sum rule. Okay. Now this piece here is always positive. Okay. You can check it. It's simply the same reason as before, because the partial waves are positive in this region. And so this quantity here is more or equal than the first piece only. Okay. And now the first piece, you can divide it between UV and IR. Okay. And then using the ratio here R, you can derive this bound. for the ratio of C3 over C2. Okay. Now, what I'm plotting on the left, so what I'm plotting first on the left is the value of R along the boundary. Okay. Now, in the lower branch, it's a fully IR dominated. Okay. So it's kind of a boring field theory that is just a weakly coupled. In the upper branch, it's close to maximally being UV dominated. Okay. Now, what I show on the right plot is the value of C3 over C2 along the whole boundary again. Okay. The red part is the exclusion given by this simple derivation as a function of R. Okay. And now the value that we found in the boundary of C3 over C2 is given by this line here, and of course agrees with the bound throughout. Okay. Now, there are other things that one can do. In the IR-dominated region, since we are at weak coupling, there's of course the hope that you can reproduce it by simple perturbative physics. And indeed, you can compute this diagram in lambda phi 4. This is perhaps not the most academic computation that we normally do, but you can still do this computation, which is to expand this at below the crossing symmetric point at one loop. Okay, a square plus this. Maybe I have a diagram later on. I have it here. Yes, you can do this computation and compute these numbers here, C2 and C3, and then the ratio, the value of the coupling, of course, cancel. And okay, you get this universal number for lambda phi 4 at extremely low coupling, and it matches precisely with the result of the Bootstrap computation. So in the IR-dominated region, we understand the field theory. It is boring theory. Now, in the UV-dominated region, which is this part here, sorry, this is this region over here. Okay. Now, what we can do is run the bounds that were done by Karen-Wald, Van Duong, and others, which consist in completely neglecting the IR part. So you neglect all the cards from the cutoff to the IR, and then you can show that positivity, only positivity, only linearized unitarity for the imaginary parts, imply these two-sided bounds. Okay. And okay, the amplitude in the region where it should, okay, in the region where it's completely UV dominated, it matches with these bounds. These bounds that were derived by assuming that the IR cuts are 0 are nice because they answer this physical setup where one asks what is the maximal value or minimal value of this ratio in a theory that it's completely UV dominated. Okay, it's not about tree level. The UV cuts can be very large. But of course, we should not interpret them as an actual bound on a theory because phi 4 completely overshoots this bound. But it's okay. This is still answering a question to a nice question. Is it clear what I'm saying?
It's absolutely clear. The mystery that is still a little bit unclear to me is how you can get the bound on a dimension 6 operator.
Okay. Let me continue.
So can I also ask a question about this last plot? So you're saying the difference between your curves and the Karen-Van Duong lines is due to the fact that you are implementing some assumptions slightly differently, and
no.
You can, what's the difference?
Yes, there's some different assumptions, of course. Yes. Let me try to repeat.
This difference is small. This difference is kind of quantifies some approximation which was implicit in their work.
Exactly. You can think it in this way if you wish.
Okay.
So the approach we are taking here is also motivated by physics, which is that we want to ask what are the maximal values of these CI coefficients for theories that have non-negligible IR cuts. Okay, the IR cuts might be small, but not exactly 0. In the limiting case where the IR cuts are exactly 0, okay, corresponds to this green band here. Okay.
Mm-hmm.
Now, now it depends on your taste, on how much you want to allow for hierarchy physics being negligible or not. Now it depends exactly on the question you are interested. And if you wish, the concession that we are making here, since I'm already out of time, let me comment on something related to this question, okay? Which is about the cutoff dependence. So we are putting bounds, no, by bounding these imaginary parts of the amplitude at low energies, okay? So what we are achieving, if you wish, is to bridge between the S-matrix Bootstrap kind of bounds that we got here and the bounds of positivity in the following sense. So the cutoff of the theory, there are two limiting cases that we can take. We can take it all the way to threshold, okay? And in this case, this bound that we are putting on the imaginary part disappears. So then we allow for like resonances all the way in front of your nose when you start with physical energies. And these are these plots here, okay? For the ON04 in this case, and for the singlet case. Now there is the other limit. When you introduce now some new physical scale, lambda, and you separate them very much. You want to take them to very large values. And this you can do it in two different ways. You can keep m squared fixed and send lambda to infinity. And in this case, if the IR couplings are moderately weakly coupled, you are left with this single scale problem of m squared. And this is a lambda phi 4, and is the region of the plot I'm showing here. Okay. Then there is the other limit, which is we still take the ratio very large, okay, but we are taking G0 to 0 first, so IR cuts to 0, and the mass to 0 as well. So this ratio it also close to infinity. Now again, in this case, a single scale problem, but the single scale is lambda, and now you get this kind of bounds of Caron-Watt et al., which are also some universal numbers for the maximal values of C2, but in units of the cutoff, not in units of the mass.
So
well,
in the second limit, it wasn't strictly necessary to take m squared to 0, right? The important
no, it's not. You are right. You are right.
The important thing is that G0 is going to 0 first at the scale at the cutoff lambda, and then m squared is whatever. Of course, it's not a single scale, but it's a small modification of the same setup.
Yes. It's not key that this is going exactly to 0. The only thing I'm saying is I'm taking the ratio large. And in fact, related to your question, this is precisely this blue curve here, okay? This blue curve here is obtained by neglecting the IR cuts and moving the mass, okay, for the cut, okay? And you see that there is some nice convergence into the massless limit. Okay? Well, this. I think I only had 1 hour, right? So this is bringing me to the conclusions. Now, the approach that we are taking is bridging between these two kind of limits. Okay, so we want to ask questions which I think are relevant for actual physical theories, where we have non-negligible IR cuts, but we want crazy UV physics, and see how much we can mess up these CI coefficients. What I showed you today was the detailed study for the singlet case, okay, of how to extract in the singlet case the small EFT region inside here, and what are some of the physics regarding the UV dominance and the agreement with Tolle and Caron-Watt bounds et al. What we are now working, and it should appear soon, is the same construction now, but with the full flavorful case. Here I'm showing already you the S-matrix Bootstrap bounds, and this already, as I was coming at the beginning, if you wish, a bound on a CH, on a one on dimension 6, but not a very useful one. And from here we should, by restricting the IR contribution, we should carve out a small region which will tell us what are the maximal values of a CH for amplitudes that have this behavior. Okay, and then we are able to interpret the CH as a roughly GH. So this is where we are heading to.
Sorry, just to ask this again, but if I'm in the second way of taking the limit, where G0 is going to 0 first,
yes, This is the bound that the one that you may be interested more.
Then are you claiming that your method allows you to still put a bound in dimension 6?
Yes.
I see. Okay.
Yes.
Thank you.
Okay. Yes. I had 1 hour, right? I think I'm done already. I'm over an hour.
I mean, we asked many questions. So if you want to take a few extra minutes, you're
okay. Well, perhaps I can show you the phase shifts 1 second and make one more comment on this slide, which I skipped before, which is that one of the nice aspects of the primal, also the dual when the gap is closed, is that you can reconstruct the full unitarity amplitude. So we know the amplitude in the boundary, so we can just plot it and stare at it. And here I'm showing you the amplitude for various points around the various significant points around the boundary. This point here, P1, the one in the cusp, and P5 here. Okay, and well, the upper branch, which is the one that is UV dominated, has this nice physical behavior where, so in the IR, it fully matches the one loop computation of lambda 5.4, and later on just does crazy stuff. Okay. In this point in the lower branch, which is IR dominated, we find like lambda 5.4 all throughout the physical energies that we can explore. And now some comment about naive dimensional analysis is that we can plot the value of C2 in units of the cutoff that we introduced throughout the boundary. Okay, and this funny curve that I'm showing you here. Okay. Now, for the weakly capped region, okay, and then we also compute the two loop contribution, okay, to C2, and then okay, in the weakly capped region, it just matches exactly even the two loop calculation of lambda 5.4, while in the upper branch, what you see is that they are like, it agrees with what you would expect with a naive dimensional analysis, that they are like roughly 4 pi, but this kind of exercise allows you to quantify more precisely, to put the order 1 numbers in this naive dimensional analysis, and also to understand which kind of physics are giving you the extremal values. Okay, but well, let me end up with this slide only that saying that that's basically the main point of what we are doing, which is first to get these I would say nice S-matrix Bootstrap regions, and then finding inside the regions the amplitudes that have EFT interpretation, but with extremal values of the CIs. Okay, and okay, I will leave it here.
Thank you very much. Any other questions?
I have a comment that from my, pH memory, I should say that I could really appreciate the contribution of the guys. That really, I think they're doing well. Not surprisingly, because of course, Joan and Andrea, they are very much into pheno. I think this could indeed this starts indeed answering the question of Higgs physics that many people were discussing for a while, but nobody knew how to address. So it seems like you guys are on the right track. Congratulations.
Thank you.
I should say that it seems, but nevertheless, I would probably, if you really want to attack Higgs physics, I would be really surprised if in this ongoing part of your work, which has ON, it's true that the case of spontaneously broken theory and the massive theory are probably similar, but I would expect that there is like order 1 difference in the result that you're going to get in the 2 cases. So maybe if you really want to address the Higgs physics, you better consider also the spontaneously broken case sooner or later.
Yes. I agree. Eventually, we would like to interpolate also with that case. I agree. For the moment, I'm content. I will be happy if we get a very similar picture as this one. Okay, where we understand precisely the massless limit of these bounds, because then it means that we are really focusing on the high energy regime.
I also had another question. So these comments that Leonardo made about the relation to the to this G0 going to zero limit. So in the G0 going to zero limit papers, usually people derive some smart equations, and then in the UV part, you just get some positive contributions, and this leads to bounds. And so this to get this positive parts requires some numerics, and that's how people get the bounds. And so you also do numerics in your own way. So is it obvious that the numerics that you are using are related to the in the G0 going to zero limit are become equivalent to the numerics that people who are only interested in this perturbative limit are doing, or is it just an expectation?
Well, your numerics are primal, the other ones are dual. So that's...
Well, we're also. Let me make a comment on. I mean, so it's a general expectation to answer your question, but we also have already some evidence of it. Okay? So this what I'm showing here, which I didn't explain all the full details, these are done with the dual. Okay, with the dual, but it's a cheap plot, but it is still I find it already very nice, because here we are only using a spin zero partial wave. So this is the Lagrange that we are trying to maximize, that we are using to find extremal values. And to get this red region, we are only using the first leading crossing constraint. Okay, and in the unitarity, we are only using this brute approximation to the circle by a square. Okay. And then for the C0 sum rule, which is given by this, we are only taking the spin zero projection. There is much more information that we could put into, okay? But if you do already this very simple, this restricted number of constraints, you already exclude all infinity, and you get this that, okay, this still has a mass gap, but sorry, a mass gap, a duality gap. But the hope is that in the next week, by just adding more spins and more unitarity and more analyticity, this will go down. But answering more concretely your question, in this approach here, the kind of assumptions are very similar, except that we are putting more linearized unitarity, but they are very similar to the works that you are referring of the G0 equals 0 to start with for this red region.
But can I also say something, because something that you haven't mentioned, but we have run the dual problem for bounding C2, including the AR cuts, but including also these additional low energy constraints.
Sure, so I didn't want to dive into this much details. You are talking about the red line here, right?
Yeah, no, I'm just saying that most of our numerics are run with the primal, but we have already some preliminary results with the dual, where we have just exploited the two-sided bounds on the imaginary part, and the fact the imaginary part on the AR cuts are bounded. And that is already enough to give these bounds, which are rigorous under these assumptions, that the IR imaginary part is small. So, I mean, what we need to do now is also to add the constraints on the real parts. And then we will really get the full dual picture of the bounds that Joan showed before. Just that.
Great. Anything else?
Hi. Yeah, I had a comment or question also, but even in the limit where you take this coupling to 0, the two problems are not the same, right? The positivity and the one that you're doing, because after the cutoff, in principle, in these numerics, you're not allowing imaginary part to become greater than 1. So in principle, this setup is strictly stronger, right? You're also inputting that after the cutoff, it can become strongly coupled, but it still has to keep the imaginary part bounded, which in the positivity games, that part is not input, right? So even in this limit,
I think the
right?
positivity bounds, they are also put the both bounds. I'm not sure I understood your question, but in positivity games, so still positivity, you are right, you will only put that. But in many of these G0 equals 0 games, they put both. They put this whole equation.
Okay.
Is it answering your comment?
But it's if G0 is strictly, I mean, the question is an order of limits, right?
Yes.
If G0 is really going to 0, then everything is going to 0, right? So the
No. Well, G0 can be 0, but then you can still have higher dimensional operator, right?
well, okay, maybe I'm saying that some of the physical assumption that you may want to make is that the entire theory is weakly coupled. You know, for example, the kind of game we play with pions, where it's large n,
yes,
everything is proportional to 1 over n. There's no doubt. It's always the only constraint you can ever impose is positivity.
Yes. That's a different limit, no?
Sort of, yeah. It's just the limit in which the entire imaginary part is small.
Exactly.
Yeah. Anything else? Okay, thank you very much.
Okay,
Sweet.
thanks to you guys for the feedback.
Thank you.
Ciao.